when we are looking at forces in 2 dimensions, just like we did with kinematics, we have to break them into x and y. We will never solve force problems with a horizontal force and a vertical force in the same equation. Okay, we never would put normal force and a horizontal applied force in the same equation. It just doesn't happen. Right? We analyze x and y totally separately. Okay? You already know how to do this with 2 exclamation points. Must have been feeling really excited about that when I made that. Okay? You already know how to break forces or vectors into their x and y components. Okay? So I'm not going to talk much more about what it looks like to be in 2 dimensions. We're just going to practice some. Because I think we're at the point now that I've told you all the basics. I've told you how to do everything. Now it's just about practicing and getting those concepts done right. Okay, because I feel like we're not quite to that point yet with forces. And so we're going to get there. Okay? So we're going to just jump right in and start with a practice problem. Okay, maybe. A force of 2,000 newtons acting at an angle of 60 degrees with respect to the horizontal is exerted on a towed car. The car is accelerated from rest at a rate of 10 meters per second squared. Find the mass of the car. So I'm going to give you a minute or two to get written down what you need, and then we need to start drawing our diagram. Too often we try to do problems without a free body diagram, and it is near impossible. Okay, so we have to start with our free body diagram. So let's start thinking about a towed car. What do we know about a vehicle of any kind? What does it have to have?
Wheels.
Why is it a towed car instead of like a frog car or like a snake car?
Yes.
Look how towed is spelled. That's funny. That's funny. You delivered it pretty convincingly. Gravity. What is?
Not the brightest.
Okay, gravity. What other force do we have?
Air resistance.
Normal force. Right? Our object has to be sitting on a surface, right? The surface is the ground. So those are our 2 kind of non-negotiables, right? It does not say anything about friction, so we ignore friction unless it tells us something about that. Okay, but we have this applied force. A force of 2,000 newtons is acting 60 degrees with respect to the horizontal. Do you know what with respect to the horizontal means?
60 degrees from X?
Right, it just means from the horizontal. 60 degrees up from the horizontal. So it would look something like this. Here's my 60 degrees right in here. And then my 2,000 newtons, I'm going to run out of room here. 2,000 newtons looks like that. Okay, does that kind of make sense what our diagram looks like? If we had friction, which we don't, but if we did have friction, would it look like this?
Yeah. Yeah.
Friction would be purely horizontal because the car is not moving at an angle. It's just being pulled from an angle. It's being dragged from an angle. So if I'm pulling on this chair upward at an angle, the friction is still just opposing the motion on the ground. Right? It's not opposing my pull. So we don't have friction, though, so we don't include that.
How did you know to draw the
I thought it was just
this way and not this way?
It says 60 degrees to the horizontal, so we want our angle to touch the horizontal axes. Okay? And that's pretty much how we'll draw, 99% of them. Is that they look just like that. Okay, the car is accelerated from rest. Find the mass of the car. So let's start thinking here. How many horizontal forces do I have? How many horizontal forces do I have? Just one. Okay. And how many vertical forces do I have? 1, 2, 3. Right? I have 3 vertical. So what we have to do here is we take this applied force, which is at an angle, and we break it into F applied Y and F applied X. Does that make sense? Yeah, you can say FAPI, right? Every class ever calls it that. It's so funny. Okay, but we break this down into X and Y. Okay? X and Y. Do you think we're ever going to use 2,000 in our problem anywhere?
Yeah. And you have to find the other side.
Right. Are we ever going to use 2,000 newtons in our problem? Is it ever going to go into our equation?
Maybe.
How many of you think, yes, we're going to use 2,000 in our net force equation? And how many of you think no? Okay, that's right. We're not going to use 2,000. Why can we not use...
Say no.
Why couldn't we use 2,000 newtons in our equation?
Because it's both, and we have to break it down into different vectors.
Exactly. We never use angular vectors in problems. We have to break it down into X and Y. So let's go ahead and start breaking that vector down into X and Y. You know how to do that. Sine and cosine.
Oh, wait, that's the...
Just like a regular vector. Sine and cosine. That's right. That's why I said 2 exclamation points. You already know how to do this. Okay, so for Y, F applied Y would be 2,000 times sine of 60, and F applied X would be 2,000 times cosine of 60.
Continue, yes. What is going,
No, we're not using kinematics at all.
no.
And it says our acceleration is 10 meters per second. Do you think this is horizontal acceleration or vertical acceleration?
Horizontal.
Horizontal, right? And so when we're looking at this problem, are we going to be concerned with our horizontal forces or our vertical forces? Only horizontal. I only care about horizontal forces because it gives me my horizontal acceleration. So we're going to start looking at what is our horizontal net force. F net.
How do you know it's horizontal and not vertical?
Well, the car's not being lifted through the air. It's being towed, which means it's being pulled.
But isn't that just 1,000 because there's nothing pushing it?
Yes, but I want to show you the full picture before we start putting numbers in, but yes.
Wait.
Half of it, yes. She's on her way. We have to set up our net force equation only in the horizontal direction. So my only X force is F applied X. Is there anything acting to the left? No, so I'm going to put in minus 0, right? My only horizontal force is that guy. Is there anything happening over here? No, right? There's nothing there.
Does that say F net X?
Right, this is my net force equation in the X direction. Okay, I would get used to writing that equation out. I wrote the 0 so that I know I accounted for there's nothing happening opposing my motion. Does that make sense? You don't have to write that minus 0, but it helps me think about, like, I thought about it and I accounted for it, right? There's nothing there. So now I can start putting in numbers. I know that my F applied X is equal to 1,000. I know that F net is always equal to mass times acceleration. What am I solving for here? The mass. I know my acceleration is 10. Right? Do we see the difference there, what I did? I started with my just variables and then I substituted in all my numbers. Right? F net is really mass times acceleration. I solved for mass. Here's my acceleration. Okay. So that means the mass of my car is 100 kilograms. Right? Mass is always kilograms.
That's not a very heavy car.
No, it's not. At all. It's like a clown car or something. One of those little, what are those called? Those little Tykes ones? Oh, Crazy Coupe. Yeah.
Oh, really?
Right. All right. What questions do we have?
Believe it or not, but...
Yeah. So I'll give you a minute to get written down what you need, and then we'll start with our diagram. If you can draw the diagram by yourself, that would be a good thing for you to try. doesn't say anything about friction, so we're not going to include friction here.
Is the machine against the slide relevant?
Right, it is. Okay, because it says it's being lifted, yet it slides. So does that mean it's accelerating vertically? Right, so here's what's happening. Almost the same scenario. I'm lifting upward on this chair. But vertically, what's happening? What's happening to the chair vertically? No, it's just sliding, right? Vertically, its net force is 0. It's not accelerating in the vertical direction. When I lift up on it, though, what am I doing to the normal force? Am I increasing the normal force or decreasing the normal force?
Decrease because it doesn't put as much weight on gravity.
Right. Okay, so as I lift, I'm taking some of the pressure, essentially, off the normal force. The normal force has to do less work as I lift upward. If I push down, that means I'm adding to gravity, which means the normal force has to work harder, right? As I lift up, I'm kind of taking away some gravity, so the normal force has to work less. So those are some things to think about. So in this case, my normal force and my gravitational force are not equal. They are not equal to one another. We're solving for the normal force here. Okay, so we talked about a couple different things. My net, first of all, let's think about this. Am I concerned in this problem with my vertical forces or my horizontal forces? Am I concerned with vertical or horizontal? What am I solving for?
F of n is vertical.
I'm solving for the normal force, and the normal force is vertical, so I'm concerned here with only vertical forces. We will, yeah, but I want to talk through how many vertical forces do I have?
3.
1, 2, 3. I have 3 vertical forces. So in my net force equation, F net in the y direction, I take my positive forces, which are normal force, plus F applied y minus Fg. Okay, does that make sense where those came from? Normal force is going up, applied y is going up, F of g is going down. Well, we add all of our positive forces. They all go upward. They're positive. Negative forces go downward. So I'm solving for this guy right here, normal force. I need to know these two values, F applied y and Fg. So how do I solve for F applied y? Right. I take 200. No, F applied y is 200 times sine of 40. And I think that comes out at 128.6.
Really?
Oh, I thought
Wait, did you say cosine or
128.56.
sine?
Okay, I just rounded that.
200 sine 40?
200 sine 40. I got 128.6.
So 149.
Are you in radians? Go to mode. So now I'm just going to go plug that in right here. 128.6. I'm solving for the normal force, so I just leave that as it is. How do I solve for Fg? I take mass times 9.8, and my mass was 50.
So it's 490.
Oh, I need to be in degrees.
Need to be in degrees. So my Fg equals 490 Newton. Okay, are we on the same page with that so far? And so what do I know about F net in the y direction? It is 0. Because my object, we established, since it's sliding, my object has no vertical acceleration. Right? It has no vertical acceleration, which means that's 0. So now I just add things together to solve for Fn. Okay, Fn. So I would add this or subtract this side and then move it to the other side of my equation. My normal force should always come out what? Positive. Good.
361.4.
So Fn equals 361.4. What's my unit for normal force? Newtons. Okay. What questions do we have with that? If there were no applied force, then my normal force would have been equal to 490. Right? But the fact that I pulled upward on this machine relieves some of that normal force work that it has to do, and it reduces the normal force to 361.4. Okay? So when my object has no vertical acceleration, my positive forces should add together to equal my negative forces. Okay, questions about that? Are we feeling better about setting up our equation? This guy?
For some reason, this seems easier than.
Try this one on your own. Please make sure you ask if you have questions. I set up my net force in the x direction by saying applied x minus 0. I substitute mass times acceleration. That's got to be something that we get used to doing, is F net is equal to mass times acceleration. In this y version, my F net was 0 because my acceleration in the y direction was 0. Right? It was not accelerating vertically, which means that's 0. Okay, my vertical I had 3 forces, horizontal I only had